Since the beginning of computing, chess has been studied as a means of proving computing intelligence. Today, we go into how computers play chess and the history thereof. Welcome to Kopek Explains Software, the podcast where we make computing intelligible.
Okay, Dave. So this week we're building on our episode from last week where we talked about artificial intelligence to do a deeper dive into an area that has really been explored by software developers and computer scientists, and that's how do computers play chess?
And this is a topic pretty close to me because my dad was both an international chess master and he also did a PhD in machine intelligence, and he did a lot of research into computer chess in the 1970s and the 1980s. Wrote a few seminal papers in it. So I've always known a lot about this since I was a young kid. I've always been learning a lot from him throughout my life. And I think chess is really seen by a lot of people as a paragon of human achievement. When somebody's a great chess player, it's seen as some kind of great intellectual achievement. I think that's one of the reasons why computer chess has always been an area of intense research, because the thought is if we can make a computer play chess well, then it's really showing that it has some human-like abilities. Now, we talked in our last episode why that might not really be the case, and how raw calculation is quite different from how human beings think and human beings learn. That said, there has been a ton of research into computer chess going all the way back to the first modern computers, and we'll get into all of that today.
I think that we should start though with why is playing chess hard? Why is this even worth exploring? What complicates playing a chess game, and how come we need computers to help us solve it, or want computers to help us solve it?
Chess is hard because there are so many possible different positions, at least hard in terms of calculation. So there's something called the Shannon number, which is something like 10 to the 120th, which is an estimate of how many possible chess positions are there. And you can figure this out pretty quickly on your own, that it's a very large number, not the exact number, just by doing some back of the napkin math. So in more simple games like Connect 4, for example, there's 7 different columns you can drop your piece into. So that means in any given position, there's 7 possible moves that can be made. Well, in chess, there's 40 or so, 35, depending on the estimate you look at, possible moves that can be made in a given position on average. That's a lot more. And an average chess game goes for about what we call 80 ply in computing. Now, there's a little confusion here. In chess, we call a move both white and black moving their pieces. But for most people, we think about a move as just one side making their move. And that's how we think about it in computing too. We say a ply is basically one side having their turn.
So
And
either
so
the white side or the black side having their turn.
is one ply, right? And so an average chess game is about 80 ply. And so if you think that in every position there's 35 possible moves that can be made, and you're going to have about 80 total positions, you can see how that quickly explodes and just becomes a huge number. So there's so many possible positions in chess that you can't just raw calculate from the beginning to the end and say, well, this is the best move in every position. There's simply too many different possibilities, even for our best supercomputers.
So, I guess then why? I mean, there are lots of different kinds of games out there and different calculations. Why is chess a good game for computers to be working on?
Well, one reason is simply because there is so much human interest. So it's one of the best studied games amongst human beings. It's been studied for hundreds of years. There's countless books, countless analysis articles, countless academic papers done about chess. It's also a really well-defined game. So there's very clear rules, and we can, within those rules, very clearly understand if a computer is playing well or playing poorly. And there's very clear criteria for what doing well or doing poorly is in terms of chess. It also has no chance, which makes it an interesting game, right? We can discredit sometimes games that have too much chance, too many rolls of the die, too many flips of the card. They might just become who can better calculate the statistics at any given time. But chess is truly an intellectual game without any chance, and it really requires deep thinking and strategic thinking and tactics. You can't just get lucky and win a chess game. So if a computer does well in it, it means it didn't just get lucky. So we consider chess a great intellectual achievement when a human being is good at it. So a lot of people said, going back to the beginning of computing, that if we can make a computer good at it, well, that's really showing something impressive. Because if it's impressive when a human being does it, it's certainly impressive when a computer does it. So chess has been studied all the way back to the beginning of computers, and for good reason, because we saw it as a great achievement amongst human beings, so it would also be a great achievement amongst computers.
When you talk about solving chess, what does that actually mean or entail?
So there's two different ways of thinking about solving a game. One way is called hard solving a game, and that means we could play it perfectly from any given position. If a game is simple enough, it is possible to hard solve it. So, for example, the game of tic tac toe, played on a 3x3 grid, only has a few thousand different possible positions, and we can hard solve it. We can tell you from any position exactly what the best move is and exactly what the outcome will be of that game with if each player plays their best moves every time. A different way of solving a game is what's called weak solving. And that's just, can we play one perfect game? Can we tell you perhaps what just the best first move is? And some games that are a little more sophisticated than tic-tac-toe, we can weak solve, but we can't hard solve. Well, in the case of chess, we can't do either. There's simply too many positions, too many possible replies to any given move early in the game. And so too many different branches of search that we can go down. And so we can't tell you in chess what's the best first move. Like we can, for example, Connect 4. I can tell you that center is the best first move in Connect 4 because Connect 4 has a small enough search space that computer scientists have been able to solve it. I can't tell you who's destined to win a particular chess position unless it's pretty far into the end game and there's not a lot of pieces left onto the board. So we can solve games that are pretty simple. We can solve chess actually when it gets down and just having a few pieces left, and they've produced what are called endgame databases. This is something my dad did some research into too. Let's say we just have a knight and a rook left on one side with the king, of course, against a knight and a bishop with the king on the other side. Well, we can't actually tell you exactly what the best moves are when there's so few so few pieces, left on the board, because there's few enough possibilities that we can do the raw calculation. But for most positions in chess, we can't. And so we can't really tell you, given even the best computing power in the world, what is the absolute for certain best move in most chess positions. And we can't even get close to solving the game.
So even though computers are so much better at playing chess than humans right now, they're still not playing a perfect game.
That's right. Yeah, even the best computer playing programs today are playing very well, far exceeding the ability of the best humans. For example, the best human grandmasters are rated about 2,800 on the ELO scale. And since this is a scale, it is proportional. The best computer programs are in the mid 3,000s. So as much as 700 points more in ELO rating than the best human grandmasters. So far and above, better than them. And human grandmasters shouldn't be beating the best computer program on their own at all, basically, in modern play.
So you mentioned in the beginning that there's been a lot of study and a lot of history in computer chess and in just the game of chess in general. Can you talk about the history of it for the podcast?
So the history of computer chess actually goes back before computers, although these early attempts are not very concrete in terms that they didn't really create a chess playing program. But the first attempt at a mechanical computing device was actually a farce. It wasn't really a machine at all. So there was something called the Turk. It was a machine that proclaimed to be able to beat pretty good chess players mechanically. And so there was this table that was being kind of taken around the world and taken to courts in the 18th century. And people would go and play this table, and the pieces would move from some kind of mechanism underneath on their own. And the program actually, or machine, really played quite well. It would beat a lot of good players. People were like, wow, how is that possible, especially since this is way before computers? Well, it turns out it wasn't possible. There was actually a human being who was a master at chess sitting underneath the table in this enclosed box and pulling levers to move the pieces. So that was kind of a bad start. But then in the 1840s, the first attempt at making a mechanical computer took place by Charles Babbage in England. And he had an assistant named Ada Lovelace who did a lot of the first programming for that mechanical computer. She's often thought about as the first programmer. It's called the analytical engine. They never were able to quite finish their computer based on gears and steam. And they actually, though, still wrote programs for it, even though they didn't finish the machine. And now in the modern day, we've recreated the machine. It turns out it probably would have worked. And maybe their computer chess programs would have worked too. But again, the machine wasn't finished. So this again wasn't a real attempt. In the early 20th century, there were mechanical machines that could do very simple endgames. For example, rook and king versus king. And this was, again, predating computers. So this was a real mechanical machine that really could play a very, very small subset of chess positions. And that was impressive, but it wasn't really a generalized machine that could play chess. So computers, of course, got invented during modern computers during World War II. And shortly after that, we saw the first real attempts at making chess playing programs. And some of the most famous computer scientists, including the father of computer science, Alan Turing, were involved in producing some of these first programs, or at least thinking about them and designing them. And so some of the most famous computer scientists, Alan Turing, Claude Shannon, John von Neumann, all were involved in early computer chess research. And by the 1950s, there were very basic computer chess programs that could look as much as 2-ply into the future, which is not good enough to beat any player of even, let's say, intermediate ability. But if you're a total novice, the 1950s computer programs might have been good enough to beat you.
Maybe in a future episode, we'll talk about some of these giants of computer science and the impact that they made beyond just their computer chess work.
Yeah, and Alan Turing, beyond being the father of computer science, is also often seen as the father of artificial intelligence. And computer chess was seen as a field of research within artificial intelligence. And so it's not surprising that he was involved in both creating the field of artificial intelligence and also creating the field of computer chess.
So when software engineers and computer scientists are thinking about, all right, I want my computer to be able to play chess, there's some debate about how to actually do that. Should they be mimicking a person, or should they try and solve it in a different way? Can you talk about that debate?
So yeah, in early computer chess, there was this big debate, which was, are we going to be able to create a great computer chess program by building one that's able to out-calculate a human being? Is that it? Is that all we need to do, basically? Be able to look more moves into the future? Or should we try to mimic the way that a human being plays by spending a lot of time analyzing strategic factors about a given position? And there were rival chess programs in the 1970s that took these different approaches and were going at one another. But what became clear over time, certainly by the 1980s, is that raw calculation ability trumped the ability to play similar to how a human being does. And so there's two different factors in a computer chess program we need to think about. One is search, and that's the algorithm you use for looking into the future. How do we keep digging further and further down the game tree towards the end of the game? And how do we do that efficiently? And then there's also evaluation. That's given some position, what factors do we look at? And these two factors in a computer chess program are actually in some ways in opposition to one another, because the more time you spend evaluating a position, the longer it takes, and therefore the less positions that you can search. So what was more valuable? To spend a lot of time evaluating just a few positions using tons of human-like factors, or to be able to just evaluate very deeply and just evaluate each position pretty quickly using just a few factors. Well, it turned out that, at least for that era, raw calculating ability was more important, and being able to search deeper was more important than being able to look at a ton of different factors for each position.
So walk us through the timeline uh, of how a computer got good, I guess, at, at
Yeah, so I mentioned the ELO rating system, which is a standard system used for evaluating human strength, and I'll kind of talk about how computers got better along that rating system over time. So by the 1960s, we already had amateur level computer chess programs. So computer chess programs that would certainly be any beginner, but they still weren't ranked at what's called 2000 ELO, which is about expert level play in the chess world amongst humans. There were bets actually about how long it would take. There was a famous bet by international master Dr. David Levy about how long it would take till a chess program would be able to beat him and more generally be able to beat masters and international master level players. It took a while. In the 1970s, they reached that 2000 ELO point where they were about at expert level. Master is 2200 ELO points. And in the 1980s, they reached that level, and they also reached international master level, which is 2,400 ELO points. By the 1990s, there was a steady progress, and they finally got to the point of being the top level in chess, which is Grandmaster. Grandmasters are 2,500 ELO and above. And famously, the world champion, Garry Kasparov, played the best chess playing program at the time, which was IBM's Deep Blue, in two matches in 1996 and 1997. And in fact, in the second match, the computer won. And so it was not until 1997, so this was after basically almost 50 years of research into computer chess, that it took to actually get to a point where a program was the world champion. So it wasn't like this happened overnight. It took 50 years of intense research, improvements in computer hardware, and at the same time, of course, computer chess was learning a little bit from human beings as well, just as human beings were learning from computer chess. So there were a lot of chess players who contributed as well to the development of these chess programs, giving advice about what they should include in their opening books, which are kind of like preset moves for the opening, giving them advice about what to evaluate in each position. So a lot went into it. But finally, by 1997, the best computer chess program seem to be at the level or a little bit better than the world champion amongst human beings. Today, now another 20 years later, computer chess programs, like we mentioned earlier, are it's undisputed that they're better than the world champion, the human world champion. And they are clearly ranked so much better that, in fact, when they have matches against top grandmasters, sometimes the computer has to give the grandmaster an advantage. Like, for example, the computer will take a pawn off the board before the game even starts, so that it's a fair match.
And we've even moved on in some ways from computer chess to some other games. I'm thinking of Go, which my understanding is that a computer has recently beat the world champion in Go, which is another huge accomplishment.
Yeah, so Go in some ways is seen as an even harder game than chess because it has an even larger branching factor. That's the number of possible moves you can make in any given position. And we had even more trouble. There was also a lot less research into it, but we had a lot more trouble building good Go programs using computer science technologies. So, we actually have now created a world champion Go program. Well, not me, but DeepMind, which is funded partially by Google or mostly by Google. And they're using machine learning techniques to do that. And we talked a bit about machine learning in our last episode. Now, in computer chess, machine learning techniques are also being used, and they are being used in conjunction with some of the older techniques for computer chess that we'll talk about. So we were able to get to world champion level in computer chess without using machine learning techniques, but it took machine learning techniques to get to world champion level in Go.
So, how does a computer actually play the game of chess? Like, what is happening?
There's really three parts to it. One is representing the position. So this is how internally in the computer's memory do we represent the position. And that's actually the easiest part. And that also involves encoding what are legal moves and what possible moves can be made in response to a move in any given position.
So understanding what the board looks like, what each piece can do, and understanding the structure of the game.
Yeah, that's the most fundamental, and that is actually the easiest part. The next thing we need to do is we need to be able to evaluate a position. So we need to be able to say, how well is this position going for black or for white? And there's a couple different things you might take into consideration there. The most important one, it turns out, for computer chess programs is material, which is simply who has more pieces, who has more pawns. The player that has more pieces or more pawns is generally the one who's winning. But there are other factors that human beings take into consideration as well, which are more strategic, such as how well positioned are the pieces, how well connected are the pawns, how much is the opponent being attacked. All those positional factors might be taken into consideration too when we evaluate a position. So this part of the program that looks at the material and the positional factors is called an evaluation function. And then the last part of a computer chess program is the search function. The search function has to go and look into the future. It has to say, well, if this player plays this move, this player can play all these moves back, and then that original player can play all these moves back, going back and forth, looking into the future. And every time it looks a little bit further into the future, it has to call that evaluation function to see, well, how good is this position? Because there's so many positions to search, right? You need to at some point say, well, this looks so bad. I don't want to keep searching this way because it's not worth my time. So I want to concentrate on the possible moves that will lead to good positions for me. And so we have algorithms for doing that. The most common one is called minimax, and it's often used with an extension called alpha beta pruning. And this is basically a search algorithm that goes and keeps looking at what moves can be played and what can the opponent play back and forth, while pruning out the possible branches on that tree that really don't lead to places that you'd want to go. And through using a search function in combination with a board representation and an evaluation function, a computer can determine, well, based on all the information I have available to me, this is the best move in this given position. So I don't think we need to get into the details of Minimax itself, but I think what is interesting is considering how far we should search given a certain position, and how do we decide how far we search. And there's a few different ways that you can go about this.
And when you say how far you search, what you mean is like how much time and how far ahead should the computer be thinking in the game?
Right. How far into the future do we go? And the issue is that chess is often played with a time limit. So in a common chess game, you might have a time control that's something like each player gets 2 hours. And then depending on how many moves are played in those 2 hours, there might be an additional hour or two added on to that time control. Fast games of chess are often called blitz, and they might be played with just 5 minutes, and each side only gets 5 minutes. And so the computer has real constraints about how much time it has to search. And how does it make the decision about how far to search and how much of its time to use up? And there are different strategies. The simplest strategy is just to look a fixed number of fly into the future. Okay, I'm going to look, 3 moves into the future. That's the simplest strategy, but that might actually not be the most effective, because sometimes when a position is really difficult, we might want to spend more time on it and actually look further into the future. And sometimes when a position is really easy, maybe we don't need to look that many moves into the future. Maybe there's checkmate in one and we're wasting our time going deeper into the future. So another thing we might do is we might search for a fixed amount of time. That's another simple strategy. And we might just search, let's say, for 5 seconds, and we see in 5 seconds, how far can we get into the future? More often, we might need to keep searching as far as big activities can still happen. And we call that quiescent search. And the idea is we keep searching until we get to a quiet position where there's no longer going to be any major changes that are really going to affect the outcome of the game. And so we might have to use a combination of these strategies. We can't just do that last strategy forever, because then we're going to run out of time. So if things keep happening, we might still have to have a fixed limit on how much time we're going to give ourselves to search. But we might use a combination of quiescent search and some kind of ultimate time limit, depending on how much time is left, to make a determination of how long to search. So we often have to use some kind of dynamic information about how the game is going and how much time is left on the clock to really decide how far we're willing to go on the search.
What is a computer evaluating, or I guess even a chess player, though in this aspect, we're really thinking about the computer evaluating to know, the best positions or what's most important or how this all works?
Yeah, I touched on some of these earlier, but I want to be more specific. So, the number one thing it's looking for is terminal positions. So, those are positions that end the game. So, for example, a checkmate, which ends the game, would be considered, well, the ultimate terminal position, right? That means we get to a point where one side or the other side has won, and so there's no point in searching any further. And if there's a move that I can immediately play that'll lead to checkmate, obviously that's the move I should play. So that's the most important thing we're looking for is terminal positions. After that, we look at material. So that's how many pawns or pieces we still have on the board. And there's a pretty common rating scale for these that humans use and that most computer programs use. Most of the rating scales go like this: a pawn is worth 1 point, each knight is worth about 3 points, each bishop is worth about 3.5 points, each rook is worth about 5 points, and each queen is worth about 9 points. Now, the really good programs today will not use this older scale, and they will have these exact point values a little more tuned, and they might even dynamically change the point values as the game goes on. So there is this rough set of points that's been used in chess, both amongst humans and computers, for a very long time. But there, in modern computer programs, usually it's going to be close to that, but a little bit modified depending on the position and on actually a lot of machine learning that's gone into recently figuring out how accurate these older point values really are. And then the last thing, which is actually the least important, but is still used and will make the difference amongst the very good programs, is positional aspects. So that's like, how connected are the pawns? How many pieces are being attacked? How many pieces are protecting each piece that's being attacked? Where are all the pieces on the board? There might be some parts of the board that we see as being more powerful for certain pieces than other pieces. How many pawns are pass pawns? How many squares in total does each side control? Is the king in a safe location? Has the player castled? All of these different positional factors all together can make a significant difference, but they're not going to be as important as terminal positions or material in the vast, vast majority of positions. So, a couple other things we touched on that a computer chess program might take into consideration or might use to its advantage are opening books and endgame databases. An opening book is basically prior data from previous games that were seen as pretty good games about how to instantly play the opening. So, a computer chess program will usually have an opening book that contains very high level play from either very strong other computer programs or strong grandmasters that says, well, if I'm in this exact opening position, this is probably the best move to do in response. The reason for this is not only does it mean that we're learning from these previous games and taking advantage of the knowledge from them, it also saves the computer time by instantly having a reply to all of these opening positions. It has more time to think later in the game. Another thing that's very helpful for advanced computer chess programs is an endgame database. I mentioned earlier that it is possible to have perfect play when there's only a few pieces left on the board. And so you can actually record what are the best moves given certain possible endgame positions. And you can have all of that stored ahead of time for the computer chess program to access. So it knows in this endgame position, this is exactly the move I can play. So both in the opening and the endgame, it is possible to have instantaneous responses from a computer chess program based on prior knowledge.
So, what's next in computer chess? Are we have we hit a wall? Are we done? Is there anywhere else to go?
Yeah, I mean, it's not possible to the best of our knowledge in any reasonable time frame to solve chess. There's just too many positions, there's too many possibilities. So that's kind of a dead end for research. There's the numbers just explode too much. There's really no possibility of solving the game to the best of our knowledge. So, of course, we're continuing to just improve on playing chess better and better and better. And using the techniques we've described today, evaluation functions, search algorithms, board representation, just those basic ingredients and improving on them, we've been able to get to beyond human world champion playing strength. We keep making incremental improvements using those older search algorithms. But what's happened in just the last couple of years has been the introduction of machine learning techniques into computer chess. And this has led to new improvements that go beyond the playing strength of those programs that are just using those traditional search algorithms. And so these are programs that, for lack of a better word, are actually learning from their old mistakes. And they're also learning from the mistakes made by human players across the board and things that human players do well by analyzing many, 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 many games. They end up using a combination of what they've learned and these older search algorithms together to play chess at an ability that we haven't seen before. And they're still kind of neck and neck. They haven't like far exceeded the ability of the computer programs using the older search algorithms, but they're up there. And there's definitely a Cold War, or it's not really, I guess it's not really a Cold War, it's a hot war between the older algorithms and the machine learning algorithm based programs to see who's going to ultimately reign supreme in the chess world. What's happened, interestingly, is that there's a lot of hybrid programs coming out now that are using a bit of both and rising to the top using the best of both worlds. There's also been interest in whether we can find a way to make humans and computers play together. So we know that a grandmaster today playing on his own has no chance against the top computer chess programs. But what might be interesting, and we're starting to see exhibition matches and even tournaments with, is a computer with a grandmaster playing against another computer opponent. The idea being that the combination of human intuition with the calculating abilities of a computer program might be better than a computer program on its own. And so we're seeing human assisted computer chess matches making the game more interesting again at that level. We also are seeing computer chess really affect the game of human chess. So human players are learning from the play of these really top computer programs and studying how they play. And there's no doubt that this has affected the way that human chess has progressed over the last few decades. Some people say it's made human chess more boring and led to more draws because the earlier computer programs, not the machine learning based ones, but the earlier ones, would always play very positionally sound positions and would be very careful about not giving up material. And so some people feel that human players have adopted that style as well and have started to play very, very safely. And as a result, we're seeing more draws. But there is disagreement about that as well.
So, is there anything else that we should know about computer chess?
Well, I think that one interesting thing to just take away from all of this is that we set a goal as human beings to make a computer play better chess than a human being. And it took 50 years, and it took some of the best minds in computer science working on it. But we eventually achieved that goal. And I think that in and of itself is a great story because it's actually a great human achievement. All the people who've worked on computer chess over the years were able to get to that point, which for many, when they started out, was seen as a great human achievement to play chess at that level. So does that mean that computers are artificially intelligent? Well, in the narrow sense of playing chess, yes. But you'll have to listen to our previous episode if you want to talk more generally about what it really means to be artificially intelligent. That said, it is a great achievement that we've gotten to this point, and I think people have been less interested in computer chess since the Deep Blue versus Kasparov matches in the 1990s, and I think people have forgotten just how much work and what a great achievement for human beings that was to get a computer program to that point.
This episode has made me actually just want to play chess, learn more about it.
Yeah, it's a great game. So tell people how they can follow us on Twitter.
So our Twitter handle is at Kopec Explains, KOPECEXPLAINS. So let us know if there's any topics you want us to talk about, and we might be addressing them soon.
And don't forget to leave us a review on your podcast player of choice, whether that be Overcast or Apple Podcasts or Spotify or Google Podcasts, whatever it is. Leave us a review because it really helps our show become more visible. And if you've enjoyed listening to us, we appreciate you helping us out in that way. We'll see you next week.
Thanks for listening.